Okay, well, good morning, everyone. Great to see you all here. Welcome to EECS 251B, Advanced and Digital Circuits and System. So in this class, we covered a lot of different modules related to circuit design, especially in thinking about different performance and power efficiency optimizations. So starting from this week, we're transitioning to, I think, roughly the 5th module of this class. We are actually starting our power and energy efficiency discussion. So we'll talk about what are the different constraints when we think about power optimization and what are some really important tricks from both architecture and circuit. We'll more emphasize on the circuit side, what are the important tricks that we can take advantage when we think about power and also energy optimization. So in this lecture, we'll start our energy efficiency discussion and with a particular focus in really thinking about power performance trade-off, because it is actually a very interesting space and different, especially prior projects have actually approached this space very differently. So well, before we start, since we're talking about power and performance, right, I find it's actually interesting to take a look at this analysis actually released from AMD in really thinking about in the past, really the past 1 or 2 decades, where is the source of efficiency actually come from, right? So of course, this is semiconductor industry, right? A lot of our efficiency actually coming from the bottom layer when we're actually thinking about advanced technologies, more TDP that we can actually support, and also bigger die area that also gives us more transistors to play with. But what's really important is I want to highlight, since we're talking about performance power trade-off, is actually the orange portion, right? Where we actually have different microarchitecture advances. We see that also contribute roughly 15 to 17% of the new performance increase across generations of processors. But very importantly, the middle tier in our orange boxes is really power management, right? How we can actually optimize with power constraint, which was actually pretty new, especially you would go like 20 years earlier, like power was not a concern. But then when power becomes a concern, like power management, how we can actually extract better performance under a power envelope become very important. If we look at back the past 20 years, both architecture research and circuit research, a lot of the innovations really thinking about how can we do better power management. So we see that's actually one of the biggest pies, especially when we think about the orange space, where now considering the technology side, really thinking about what we can do in hardware and circuit, power management is very, very important. So with that, and especially we don't have the time to actually cover in this class, like I also teach a like domain-specific hardware class, especially when we come to domain-specific architecture. One of the major motivation for domain-specific architecture is actually the power problem. We cannot actually power all of the auto-order fancy microarchitectures with the current power budget, so we want to actually use our power budget more efficiently. So if you actually understand power, you can actually see basically the reasons of the transitions in the past 20 years, why different companies, why different designs actually make certain optimization. So this is really very fundamental when we actually approach, especially modern designs. So with that, let's get started when we think about low power design. So first, let's start from the basics, right? So whenever we talk about power, there's always 2 things, right? One is energy, one is power, right? Of course, a lot of time we actually lump them together. They are definitely related, and we'll actually see more later, but they are also different from a very high level. Energy is very important when we think about a mobile device, right? How long our battery can last, right? Whether our phone can actually last for 1 day, that's become actually a challenge these days, right? So for mobile device, portable device, energy is very important. That actually determines how long we can actually use our device, what's the total amount of computation that can actually be performed. Eventually, we'll see actually for both power and energy, especially today, when we actually see a new announcement, it's always how much better performance we can deliver, right? So that's what I mean when we think of power optimization. It's always given a power envelope, given a power constraints, how we can actually maximize the performance. So that's always the question we're trying to answer here. So when it comes to energy, performance is still very important. That also applies to power, but with a different angle, right? Power is really about the rate of consumed energy, right? Especially for some of the high performance performance crucial applications. I'm not sure whether you folks are following today. This year's ACM Turing Award is actually awarded to actually HPC expert, really thinking about high performance computing, right? So this is very important because we need to think about what's like highest performance we can deliver and how we can actually set up our cooling infrastructure to actually cool down those energy actually burnt, right? So a lot of today's design is actually very power limited. I was reading the new NVIDIA 3090 Ti announcement, their latest GPU announcement. The entire board, the power is 350 watts. It's crazy when you think about it. It's actually a gaming GPU actually need to be actually plugged in a desktop, and then it's already get to like 350 watts. So that's basically a single GPU card, right? So that's a thermal power budget what we're talking about today. So very important. There are a lot of innovation we're trying to do so that we can effectively cool down the system. Again, we still want to, under a power envelope, deliver the maximum performance. So performance still very important. What is the slide show? Performance will sell the product, but energy and the power become a very important constraints when we think about today more than optimization. Well, this wasn't true actually. You may actually go back roughly 20 years, right? So before we actually run into the power problem, performance is actually always the key, right? We always just only care about performance. We never actually worry too much about power. We'll talk a little bit some like how Denner scaling actually helps us in that regard. But performance is always the key. So I was actually digging through some like performance like around the 2000, right? So I have an EECS paper there. Back then, a lot of discussions is really thinking about how deep we can go with our processor pipeline. We really want to go super deep with basically each pipeline is very few computation actually going on so that we can actually get clock at a higher frequency, right? Because each stage is so short. And if you look at basically before 2000 here, right? It's actually crazy. Just think about like the clock delay. We're talking about roughly 7 or 8 out of 4 delay. That's actually crazy, right? If you think about flip-flops, that's already 2 or 3 there, right? There's not a lot of computation. It's actually very deep pipeline, not a lot of computation going on. So that's basically we're going when we actually projected to reach roughly like 2 gigahertz. We're talking about just like really just a couple of gates per stage to actually get very high frequency. So that has always been the focus. There were like a lot of study, even when we think about optimal pipeline depths, it's more about how we can actually offset branch prediction latency, right? If it's too deep, besides the power, right? Power is a big concern, but there's all performance, right? It's too deep, the branch prediction penalty will be very high. So a lot of the trade-off is still very heavily focused on the performance point, especially from architecture. So here, this is basically all the crazy architecture ideas reach us basically very, very deep pipeline. At the circuit level, again, very similar motivation. We really want to maximize performance. We want to lower our threshold voltage. We want to actually switch as fast as possible without really consider power consumption. That's also what we actually want to do at circuit level. So a lot of like we talk about the logic effort, how we actually size the gates, again, very performance oriented. So that has been basically the philosophy roughly 20 years ago. And it was true for a while. That's how we actually get very good performance, but things actually changed, especially with the end of Denner scaling that actually completely changed the landscape here. So what exactly has changed, right? So with the help with Denner scaling, right? We really like Denner scaling. It's really sad. I was like reading the comment about the NVIDIA 3090 Ti because it's reached like 350 watts, and people are saying, oh, we really miss Denner scaling because with Denner scaling, we don't need to actually have consume so much power just to power a GPU card. So Denner scaling was very important in terms of actually driving down the energy cost, right? Why it helped, right? So with the traditional scaling model, follow Denner scaling, right? So you will say, let's say VDD scales by 0.7% and frequency, basic performance scales like 1 over VDD here, right? 1 over 0.7. So with performance actually go faster. You will actually calculate the power, right? So power is CV squared F here, right? So different factors here. Let's go backwards. from F, frequency is higher, right? Our transistor is smaller, we can actually switch faster, so frequency is higher. Voltage is also, voltage is actually lower, right? Because we're lower voltage here, we can actually also get lower voltage. And it's very important, we'll actually come back to this. Voltage is a quadratic relationship, especially with energy. So that's very important. And the capacitance is also getting smaller, right? Because our device is smaller, right? The dimensions get smaller, our capacitance is also getting smaller. We do have one factor that's actually getting bigger, right? So this is actually more associated with area, right? So if we actually make our capacitance smaller, the die area, we actually still want to have bigger dies, right? So the die area actually has been increasing in the past, right? So we can actually afford more transistors here. We have bigger die, so we do have a bigger die area. So then the power kind of increased mostly due to the die area increase. But what's really important is the power density is basically power divided by area. And this is constant, right? So that's basically the idea of linear scaling, power density is constant.
Now on the equation, I think the cap is actually increasing because it's 1/0.7.
Yeah, so the cap per unit is decreasing, but this is the total capacitance. So this is the total capacitance because we need to actually multiply with die area. Yeah, so the capacitance is increasing mostly because from the die area, but the power density, again, the promise from the linear scaling is really the power density, power per area is actually constant. So that's basically the ideal world we want to live in, right? We just keep the scaling going, and then we actually don't need to worry too much about the power problem because we actually have the constant power density. Well, that's the ideal case, but people are always super ambitious, right? Especially when we come to the semiconductor industry, we always want to squeeze more performance with the existing technology. So you look at the past trend, right? So instead of actually scaling by 1/0.7, 1.4-ish, our frequency actually go a lot faster, right? So let's say our frequencies actually go faster, like more like 2x going up. So we actually do get actually higher power consumption. So that's basically the trend, especially before 2000, right? Even with standard scaling still true, but we are actually scaling frequency really aggressively to get better performance, especially I remember when I was a kid, when I was like looking at the computer, it's always, oh, who actually get the first 1 gigahertz computer? That's always very important. And then AMD did it first, and then that's like make a big deal. So it's always this frequency game, right? So everyone is pushing super hard with frequency. So we went at very ambitious. So actually the frequency actually increased much faster than expected, and we also get higher power. What's the really issue? Why people actually miss standard scaling is with the end of standard scaling, we cannot keep actually scaling down voltage anymore, right? We need to actually maintain a certain threshold voltage and also maintain our leakage consumption. So with that, we cannot actually scale voltage as fast as we like. So with that, we can actually, the voltage actually need to be scaled slower. We need to actually keep our voltage VDD at a particular rate. So with that, voltage scaling is actually slower. We actually still scale frequency pretty aggressively. So the power really exploded because now we cannot scale voltage faster. And then if we keep pushing this whole frequency envelope, right, the power become really a problem. So that's basically the rationale, right? When you hear people say, oh, we missed standard scaling. Why? Because we like the constant power density, right? If we just follow the roadmap Bob Dennard actually laid out, we don't have a problem. Then people are ambitious. We're actually scaling frequency faster. Then we hit a wall of voltage scaling. We cannot rely on that. So both actually makes the problem even worse. So this is an Intel projection around 2000, right? While people actually realizing the problem, right? So now we cannot scale voltage as much as possible. And then if we keep this rate of scaling frequency, we are going to have a huge problem with future generations. So this is projected, right? After 2000, all of this is projected. We keep actually pushing this way, we will have a power problem because all of the power is like, we're not even talking about watts, right? We're talking about kilowatts, right? It's more like appliances instead of processors anymore. So this is a huge problem, and people kind of realize that very late, around 2000. So this is basically the beginning of a lot of power energy optimization in both architecture and the circuit, because we realize this is a problem. We cannot keep pushing for that. Again, this is more like a projection, right? What really happened? Well, it's bad, but not as bad as this, right? So many of you have seen this, right? So in different perspective, but if we actually look from more power-oriented perspective, this is around 2000. This is basically when we realize that we cannot keep pushing the power envelope anymore, and then the power roughly kind of plateaued around like 100 watts, right? So even today we're talking about 200, 300 watts for our CPUs and GPUs. So even the density is increasing, right? So we still get pretty good density of transistors, but the power definitely plateaued. And to actually minimize the power, one of the transformation or design decision we did is basically start from the multi-core processor. So we don't go to super deep pipeline. We also cut basically the wire capacitance. We don't actually have a lot of long wires in our chip. So all of those actually want to design to actually reduce overall capacitance, reduce overall complexity, so that we can keep this particular fixed power envelope. And also, like was saying, we'll talk a lot is the frequency and the voltage, and then frequencies roughly stay the same in the past 2 decades, really. So 2000 is really important time frame when we actually have this transition, realization that we cannot keep doing what we used to do, right? So the new design philosophy is basically the whole power-aware computing, energy-aware computing, right? So maximizing performance is just not realistic anymore, right? We cannot just keep only optimizing performance. That's not fabricatable. We cannot actually keep doing that. And what's really important is people are always very greedy. It's not like, oh, power is important, let's just completely optimizing for low power. It might be true for some like low power applications, but in a lot of cases, we still care about performance. We like to extract performance under a particular power or energy envelope, right? So that's always important. It's not like, oh, we just go to the minimum. In some we'll also talk about that later. In some scenario, that is a case. Like that's just really highlight, emphasize on power, energy instead of performance. But in most of the cases, we still like to actually still maximize performance. So that's still very important. If we do actually have some actual performance, we can actually use for power energy reduction. So for some scenario that we care less about power, about performance, or just as long as we process in a particular rate, right? The sensor come in, let's say at 60 frames per second, as long as we can process under 60 frames per second, we're fine. So that also particular scenario that we do emphasize more on energy instead of performance, but in most of the cases, especially processor design, performance is very, very important. Yeah, so now we come to this trade-off, right? So now instead there's always optimize for performance, let's try to do this trade-off between energy and the performance. So with that, we're going to cover a little bit more the different things. When we say power, what do we mean by power? When we say energy, what do we mean by energy? What are the different metrics are actually being used to facilitate our later discussion? So we'll start from energy, right? So this is very more intuitive, right? We talk about battery all the time, battery on our phone, battery on our laptop, right? All of those is actually very important. There's not much change really in battery technology. Again, it is always important. I think we're doing again much better than like 20, 30 years ago. We have a lot more portable devices. So that's definitely very important, but it's definitely not scales at a more like exponential rate, right? So even exponential rate, not every year, it's more like every 10 years. Like I remember in my grad school, one of the projects we're doing is what we call like Robo Bee project, is making like very small, like bee-size robotics so that it can actually do a range of different functions. And on the EE side of things, of course, there are lots of challenges on mechanical engineering processing, but on the EE side, the huge problem is actually how we can actually design battery for this kind of devices, but it has always been challenging. So in the end, we can only basically with battery powered, it's almost always need to be tethered. So it has external power source. If actually it need to be battery powered, it can only fly like 3 or 5 minutes. That's about it. So battery is very limited, but again, things are changing, but not at a faster enough rate. But really energy is about the total energy stored in battery. Yeah. Power is a lot more diverse, right? So that's a challenge when we actually talk about power, right? Different people talking about different things. What exactly do we mean by power, right? Power consumption. There are also different aspects of power, and they're related, but they are also subtle, right? So that's always very important when we approach power, what exactly we mean by power. So I find this kind of curve very interesting because it actually summarizes different components of power. We'll just go through them. So basically here is basically power over time plot, just capturing different power consumptions while the application is executing. So the first one, let's start from top to bottom, right? The first one, the purple one, is basically almost the highest one. It's basically what we typically mean max power, right? Sometimes if you are doing the tape out, typically we always like to say, prepare a power virus test, right? So you can actually extract power to see what is the maximum power that can be extracted. So this kind of power virus tests are not really like real applications. Typically some kernel that you actually designed tailored to actually maximize the chip resource usage, making sure everyone is switching, right? But this is specifically give you an idea of the maximum power that can be consumed on the chip, right? So that's basically the maximum power trace. We also really care, especially from a hardware evaluation point of view, right? Maybe it's not actually very applicable in terms of how it's in the regular representative use case, but this is very important in terms of understanding the overall structure, right? Artificial code actually generating the maximum activity, especially if you're actually doing some kind of processor, have some digital component, it's actually very important. It's also for debugging purpose. I always like to have a power test, a set of power tests actually, virus tests ready so that we can see the maximum power. So this is more like artificial, right? In more practical way, we actually really care about real workload performance, right? So then the green one, we actually see more variations, there are ups and downs during the execution. Those are actually more applied. This is like application power traces, right? Application power consumptions. When it comes to application, again, there are phases, right? It's very hard to actually say the application is always running at the maximum frequency. If that's the case, you'll have a very interesting application. There needs to be something you can do with it. But typically, when we actually come to application, there are ups and downs, and we'll actually come back to this, especially when we talk about DBFS, right? So a lot of optimizations, both at architecture level and circuit level, is basically leveraging this kind of ups and down behavior, this kind of phased behavior in application that we can actually optimize for about better performance. So this is basically application behaviors. Again, very important. This is actually a lot more representative if we are evaluating a real product, right? What is the practical applications and what are the representative performance here? So that's the worst case. Oh, horizontal is basically time. This is power consumption over time, right? So that's a good question. Yeah, so this is power consumption over time. So that's why there are like kind of the phased behavior, right? At different time, you actually may have different behaviors. So that's a good question. So when it comes to time, right, there's also different granularity of time, right? So that also can actually affect when we actually talk about different power here. So the green is basically the worst case, very fine grain. We're actually capturing the power transition up to this almost like cycle level, which is very low, right? Sometimes you will also hear people talking about transient power. So transient power is actually pretty close to what the green curve is trying to show. It's basically like tens, sometimes hundreds of cycles at the most, right? So it actually follows the application fairly well, right? So this is at the finer granularity to actually capture the application's behavior. And then like thermal power is actually something we actually see a lot, especially when we read a TDP, right? That's basically the thermal power budget, right? So this is actually, so typically at coarser granularity, more like seconds now instead of nanoseconds that we see before in transient power. This is actually more affected by your cooling technology, right? How fast you can actually cool your power consumption. So a lot of way, especially when it comes to package, right? So that's thermal power is really important, is what's the cooling structure you have and how fast you can actually cool down the power. So that's again at the coarser granularity here. So finally, another case you may hear is really average power, right? So average power is actually more associated with energy, right? So it's more like, oh, here is the total energy over a period of time. Let's average it. Let's get the average power. So typically, we actually use average power more together with energy because they are actually more closely related. Again, this will be even coarser granularity, and in this particular example, right? Again, we have up and down behaviors in our application, but then we actually averages them out in very coarse granularity. It's very flat. So it doesn't really capture the like the real-time behavior. It's more like energy. It's actually capture the application behavior over a period of time, right? So yeah, power, again, power is a very interesting metrics, and people talk about power, but they actually mean different things. Max power is important to understand the chip behavior. Application power is more representative, and this kind of phased behavior is very common. That motivated a lot of the circuit and architecture power optimization to take advantage of this kind of more phased behavior, so that we can shut down or like lower power during those valleys because they are not consuming much, but then maybe get a higher frequency and voltage during those peaks so that we can actually make those run faster. Right, so those are different power behavior, the different terminology people are using when it comes to describing power. So again, just one last note, this keep comes back. I think we have already been talking about that. Power is more like a rate of consumption, while energy is really like a total actually energy being consumed, right? Especially when we actually compare different techniques, always keep that in mind. Like this is actually similar to what we see before, right? We're looking at the power over time, right? So in this case, power is really the amplitude, right? The height of the curve, right? So different approaches, different optimization may reach different power consumption, but they may actually have the same energy benefit. They may have the same energy cost because energy is really the area under this curve, right? Power over time, right? So energy is really the area over time. So those different techniques, sometimes they are transferable, maybe get lower power and then also lower energy, but sometimes they are actually very different. We don't see that a lot, and it's more like just less popular, but still important. Before, like if you talk to IBM, all they care is about power because they are building this kind of high performance computers, and they really need to care about power, making sure they deliver high power for those applications and making sure their power delivery network can actually sustain those high power consumptions from their application. But when you talk to like mobile market, Qualcomm, Apple, and then it's actually a lot more about energy because battery is a lot more important, right? So again, different market also have different focus here. So that's power and energy. Some of you may also wonder, oh, well, we actually see all the random papers in this space or random optimization space. They don't only talk about power or energy, right? There are all the weird metrics they're using. Well, they are kind of weird, but not necessary. They're also useful, right? Let's also just clarify that so that we understand what we mean, right? When we talk about different metrics, right? So the first one is actually basically when you hear people talking about energy delay product, it's basically energy. I'm sorry, power delay product is basically energy, just like a fancy way of saying energy, right? Because we're basically doing power multiplied by delay, right? So this power delay product is basically energy. So that has the same trade-off as we mentioned before with power versus energy. Another one you will hear a lot more often, we'll actually talk a lot about energy delay product because this actually shows this kind of trade-off between the total energy actually being consumed and also performance that we benefited from the energy, risk from the energy consumed. So this is actually, especially when we come to the trade-off, right? Whether we actually want to highlight more thinking about energy consumption or we really care about performance. So this is a trade-off that we see a lot in a lot of hardware design and trying to actually balance the energy and the delay product. So that's the middle one. People actually, you may also hear people actually propose like more random stuff, especially sometimes it's like energy delay square product. It just have so many different metrics here. So this is also especially in I think 2000 when it comes to actually optimization, especially optimizations that are independent of voltage or voltage scaling, we'll see a lot of people actually talking about energy delay square product. Well, why do we want so many different formula? I guess this can keep going. And people actually talk about the delay to the power n or energy to the power m. You will see a lot of metrics. So I don't actually go through all of them. This actually keep coming with all the different metrics. In particular, this one, the motivation is really we want to have something actually independent of voltage. So one thing is really important, especially when we think about energy and delay and when it comes together, right? So energy is CV squared, right? So this is basically quadratic with voltage, right? So again, voltage is a very powerful tool. So that's why people come to this metric because they want to have voltage independent metric, right? Delay is basically 1 over f, right? So this is also more linear with 1 over voltage here, right? So the problem with, if we think about, if we just do energy delay, right? Energy delay product, it will be basically V squared for energy and 1 over V for performance. So this will basically be highly dependent on voltage, right? If we just focus on the energy delay product. What people find is that sometimes we actually spend a lot of effort actually doing either architectural or circuit optimization to actually optimize for better energy delay. But then you would just switch voltage, we actually get better benefit because voltage is such a powerful tool here to actually understand, to actually trade out in this space. We'll see a lot. And in those cases, right, if voltage scaling actually can do that, why do we actually spend more effort doing all the different fancy things instead of just simply scaling down voltage? So this is very important with this voltage dependency when it comes to energy delay product. So that's why people actually propose this energy delay square, right? So with delay square, so this will be also an inverse quadratic relationship with voltage, right? So this is really just want to get a voltage invariant metric so that we can really focusing on the optimization, either at the microarchitecture or circuit level that's actually independent of voltage so that we can actually get a better idea whether it's actually even worth doing this optimization, right? If voltage scaling can do it, we'll talk more about voltage scaling. It is a very important tricks in actually metric and also optimization area when we think about delay optimization. But the whole idea behind energy delay product is really, let's make this metric. Metric is always, because metric drives the decision, right? We want to have a metric that is actually invariant to voltage so that we can actually focus on the idea. So those are the different metrics we're using, right? Again, power delay is basically energy, right? So it's still power and energy. We use energy delay to understand the trade-off. We'll talk about the energy delay characteristics because voltage plays a very important role. We'll also see that actually impact the overall trade-off. But then in a lot of optimizations, we want to have something actually independent of voltage. So that's why energy delay square is actually be used a lot in, again, it's still popular, I guess it's still important, but it was super popular in 2000 when we actually started doing the exploration. Right, so those are the metrics that we're using. Questions, comments? Okay, right, so those are the metrics that we care, the metrics that we are using to evaluate this, right? So we talk so much about power and energy, right? So where does power go, right? Where is the source of power consumption in CMOS? We have, many of you have already seen this, so we're not going to spend too much time on this. Again, different components, right? So dynamic power, the first switching power, right? So that's what we discussed, right? CV square F when it comes to power, right? So we need to charge and discharge transistors whenever we actually switch our circuit, right? So 0 to 1 or 1 to 0 transition. So that's very important. Also typically this is also be viewed as dynamic short circuit power. So this is especially in CMOS. Is basically during the transitions, there could be a transient period of time that both CMOS and PMOS, both PMOS and NMOS are actually up, right? So that's why it actually triggers short circuit power. It is actually getting not, it used to be a big issue. There were a lot of optimizations to work around short circuit power, right? But it's getting less important, especially more advanced technology, right? Why is that? Why is it actually getting less important with for short circuit power? Hyun-suk?
Yeah. Okay. I think because leakage is more important.
Yeah, leakage is important, but this is not even just percentage-wise, not important. It's really even just absolute term. It's actually not very important. Ken? Yeah, related. Yeah, as Ken mentioned, the circuit is actually so fast now, right? It's actually be very very unlikely both NMOS and PMOS are on. It's also related with voltage, right? So VDD here. If the voltage is actually very low, all right, so to have actually both those on, right, we need to both, basically the gate voltage for both PMOS and NMOS need to be actually bigger than the threshold voltage, right? Now the threshold voltage is relatively constant, and then the VD is actually getting smaller. So it's actually very rare to have the voltage that are able to actually turn on both PMOS and NMOS. It just, with the voltage scaling, threshold actually doesn't scale, just very hard to turn on because this require both need to be on, right? So this is a side benefit with scaling doesn't work. We cannot pull down threshold voltage anymore. So it's a side benefit that we can basically not turn on both of them. So yeah, so people still talk about short circuit power, but and typically you will see the report, they basically lumped together with the dynamic power, but it's less important, especially more with advanced technology. So Hyun-suk is right, the leakage power is still very important, right? So again, different people have different rule of thumb. These days, people typically think, I guess 2/3 of the power is actually dynamic power, but 1/3 of power is actually leakage power. This is a pretty, again, we're talking about iteration principle here, right? We'll see a design where actually spending a lot of power actually spent on leakage power. Again, we'll talk more about the trade-off, especially scaling voltage, right? So there is also a trade-off between performance and energy, right? Also between dynamic and leakage, right? So if you have a high voltage threshold, right, you will have like smaller amount of leakage, but your circuit will also switch slower, right, because your threshold is too high, right? But if you have a lower threshold voltage, and then you will switch faster, you will have higher dynamic power, but then your leakage will also be higher because your leakage power will be higher because now it's very leaky, right? So different people have different optimizations. If you really care, want to minimize leakage power, you may choose some high VT device. If you really care about the dynamic, you want to be faster, you may choose some low VT device. But then to drive some more balance, leakage power is actually very important. It's actually a very significant amount of energy is actually spent in leakage these days. So there are benefits and also disadvantages of technology. So we get rid of, not completely get rid of, but short circuit power is not very important these days, but leakage is very important in optimization. So yeah, so when we actually approach the power, right? So this is a typical, again, power is really a rate of energy consumption. It's has both a dynamic component and the CV²F. Again, one thing is actually very related to the switching activity, right? We'll see more how we actually modulate based on the switching activity there. But then the static power is also getting a lot more important these days. This become a very significant part of the power optimization. So that's a basic of different power metrics that we're using, different trade-offs in this space, and different components of power, sources of power that's actually being evaluated. In the next couple of weeks, we'll actually go through some of the techniques we'll be using to drive the power, to try to minimize the power, or to understand the space, and also take advantage, especially remember the phased behavior that we have seen. A lot of circuit optimizations actually try to take advantage of that. So before we get there, a little bit more on the space, since we're talking about the optimization, right? Again, a lot of today's tools are actually doing really good, doing some kind of understanding this kind of trade-off, doing some kind of this kind of optimization internally. But again, it's important to also develop principles, understand the trade-off in this space. So next, we're going to talk a little bit more about the power performance trade-off and metrics involved that relate. Before we move on, questions, comments, thoughts? Okay, a couple related actually announcement. So Eric will actually be doing a Joule's tutorial, how we can actually do RTL level power estimation in this week's discussion, this Friday, basically tomorrow. So definitely stop by. Again, I think most of our analysis so far is actually doing gate level analysis, which is very accurate. But sometimes, and also some of the projects actually want to do this kind of fast power and energy estimation. So Eric put together a Joule's tutorial so that we can actually do RTL level power estimation this Friday tomorrow. So definitely stop by the discussion. Some of you may actually will use it directly for your project. Even now, it's also something nice to keep in your toolbox. And when you start your project, if you want to have some fast power estimation instead of going through all the synthesis flow, you can also take advantage of the RTL power estimator there. And I see most of you have already submitted the midterm report. So we're in the process of reviewing that. If there's any significant change with your project, definitely reach out to your faculty mentors and also schedule meetings there. We can always happy to have a discussion. Okay. Well, no more questions. We'll start the discussion in really thinking about the trade-off. So this is actually this type of optimization is very popular in early 2000s. Basically trying to understand different metrics, different factors that affect the power performance trade-off and how we can actually optimize this, right? So what do we mean the power? Sometimes you'll see people talking about design space exploration, right? What do they mean by design space? Typically their device space is like energy and performance, right? So overall, we want to have lower energy, the lower, the better. So here we're plotting the delay, right? So delay is also the lower, the better. So this lower left corner is where we want to be, but typically it's very hard to be that, right? So if we want to minimize delay, typically it has some very high energy consumption. If we want to lower the energy consumption, again, typically we need to actually we have some low delay that we need to take, right? So this we see again is still important, but it's interesting. I was talking to Bora, so he was saying like in early 2000s, a lot of ICC papers are basically doing this kind of optimization using either VDD or sizing multiple tricks to actually figure out what's the optimal space. And the architecture is doing the same, right? All the different pipeline depths, all the different parameters, the cache size, like width of different units, and also trying to understand the space. So it's very popular to understand basically the sensitivity of the different design metrics and how we actually navigate this space, right? This the energy delay space to actually understand the design. So what do we mean by different space, right? So I already hinted earlier, right? So especially like we think from like more architecture space, right? So this can be like two different microarchitectures, right? With the different, again, like voltage or sizing parameters, they may actually have different trade-off, right? And then depends on where you are, right? If you want to something actually high performance, again, the lower the better, right? You may actually pick microarchitecture A, right? But typically it's deliver higher performance, or if you really care about low energy, right? You may actually pick microarchitecture B. So this was more abstract again in 2000, but some of you may find this very familiar if you actually read the announcement from either Qualcomm or MediaTek. These days they're doing what they call big little, right? Now it's actually more like big, middle, and then little. It's actually getting crazy with all the different architecture. They have big cores, small cores. Now they have actually the MediaTek announcement actually have big cores, medium cores, small cores, right? So all of this is basically, sometimes people call it big core like AP cores, and the little core is like low performance, sorry, low energy core, right? So a different name to this, but this is basically try to take advantage this trade-off, right? Because of course it's a trade-off, but also something very fundamental, right? You will have, let's say this will be very likely out of order core, and this will be more like in order core, right? So different cores have different behaviors. It's really hard to cover both the low energy space. So this will be low energy space and also high performance space. It's really hard to cover both, right? And then with that, so this basically motivated a new generation, a whole generation of this kind of big little architecture. Now it's more like big, middle, and the little, big core, medium core, and the little core, right? So we see this kind of design almost standard in the mobile SoC these days. So that's basically an outcome from this kind of energy delay optimization happening in the 2000 range, and then that actually leads to this. We'll see a more recent study understanding this trade-off, but this is a very interesting shift. Instead of like homogeneous architectures, we're actually talking about all the different heterogeneous architecture. And then eventually, depends on how we do that. I think sometime people also do this way. This is more like accelerators. So they are actually able to push the envelope further and closer to the optimal region, right? Because it cuts a lot of the energy overhead of the accelerators, but also deliver performance, right? So we talk about this kind of big little architecture now, a lot of like say neural engines, all these kind of things. Our SoC become very heterogeneous these days. It's basically again related to this trade-off, and then how we can actually get better performance, get better energy efficiency with different architecture. So this is architecture level, right? We'll also talk a little bit more. This also exists in circuit level. Again, this kind of analysis has very interesting implications in today's microarchitecture design, and that basically lead to this kind of heterogeneous architecture these days. So that's a trade-off. But like more specifically, right? How do we actually navigate this trade-off, right? So again, let's say we start from somewhere, this unoptimized design. Again, the lower the better, right? We want to have smaller energy consumption and also lower delay, right? So this is basically the ideal scenario. But typically, it's actually very hard to do this. What typically do, I think what we mentioned earlier, right? It's more like either having a particular energy envelope, right? Let's see, this is the max energy we can consume, and what's the best performance we can get, right? So this is one of the design points. Or sometimes people say, oh, this is, we need to at least achieve this delay, right? Let's just find the most efficient implementation to actually achieve the delay, right? This may seem abstract, but when you actually approach your design, this kind of decision show up a lot. For most of the hardware design, CPU architecture design, it's more like this. We want to, let's say there's a particular energy envelope we want to hit. Let's find the minimum design that can actually achieve that energy. So in most of the designs, it's more like this. So it's still pushing very aggressive in thinking about energy and minimize delay, getting better performance. For this style design, it's less showing up in processors, but showing up a lot when we actually need to interact with sensors. There's a particular rate that you need to hit, especially a lot of microcontrollers. You may wonder, like microcontrollers actually haven't advanced actually as fast as processor, right? It has been basically, it's still very, very interesting, very nice, can do a lot of things, but they haven't actually advanced very fast because it basically, as long as you can meet the sensor's requirement, right? So then this is basically all you can do. If you can process faster, it's nice, but you don't have to, right? So for that kind of domain, it's actually very different optimization. For those, typically, okay, this is a rate, the sensor come in, just making sure that we can hit the rate. We recently started some project on the robotic space, and it's also really interesting to see this kind of two different optimizations here. So this is basically the microcontroller. This is actually also showing up in robotics. So this is actually interacting with sensors. So this is just use microcontroller. It doesn't need to be actually super fast as long as we can get the sensor data processed. So it's fine. And then, but microcontroller actually also feeding data to what they call companion computer. So companion computer is actually more like this, right? Companion computer can do a lot of things like perceptions, localization, right? All of this actually is always the more performance, the better, right? This is a particular energy target we have, but we do want to get the more performance, the better. So that's also like microcontroller actually do some processing and feed the data to the companion computer, and the companion computer start doing a lot more complex processing, and then it's always the faster the better, so we can actually navigate the environment better. So those two design scenarios do show up when you actually approach your design. So this may seem abstract, but I want to give you a more applied flavor to it because both are important. In most of the cases, we're giving the energy, trying to minimize the delay, but there are cases just get a delay, get your performance. All you need to do is get this target, then you are done. So this is the optimization, right? So yeah, so I mentioned like a lot of cases, most of the processor design is basically achieve the highest performance under the power budget. In a lot of cases, right? So when we actually talk about performance optimization, it's not only just a single design point. It's more like different curves, right? So we talk about VDD. Right, so different VDD will give you different energy delay trade-off, right? So that could be maybe one curve there. Maybe another curve, we start from this random design, it was circuit level, right? So this could be another curve that actually have different, let's say, sizing. Right, and the different sizing, it will actually also give you different curve, right? Let's say there will be another one, more like topology. Like circuit topology, right? Like we're designing adder, right? Whether you're doing a ripple carry adder or carry of the head adder or carry select adder, right? Those will also give you different curves. There are different options here, and different options have different behaviors, right? So this is actually a multi-variable optimization problem, right? How we can actually understand different variables question.
So I understand that Emacs and Dmacs are fixed by the requirement of application of the specs, but what is deciding EMIN and DMIN?
So I see. So Emacs and the Dmacs is basically the spec, right? So this is what the spec we have. The question is, how do we know what's the EMI and DMI? So the EMI and DMI, this minimum one, is basically we know from this curve. So we didn't actually talk too much about this curve. So typically people call Pareto frontier. So this is basically consider all the different design optimization you can do. This is as much as you can push. This is basically the best you can push. Given a particular delay target, this is basically the fundamental intrinsic behavior of this circuit. This is the only minimum delay minimum energy it can assume. We cannot go any further. Just consider all the tricks that we can do. This is a Pareto frontier in terms of this is the best we can do. We cannot do any further. So EMI and the DMI, this is more like implication. Given this design, given these constraints, this is best we can achieve. We cannot do any better. So this is more, so you're right, this is more come from spec, right? So this spec will give you the constraint. This is basically very design specific, right? Because this is different Pareto frontier represent different designs, and if we are given this Pareto frontier, this is basically the best we can achieve. We cannot do any better, right? Right. So that's a good question. So this is basically, yeah, as we mentioned, there are all the different parameters, right? Like VDD, different sizing, topology, like we also mentioned earlier, right? This could also be micro architecture, right? So there are all the different individual parameters, but if we actually group all those parameters together, we'll get this, what people call, we'll hear people call Pareto frontiers. Basically, consider all the designs, all the random designs we have. This is basically the best we can do under a particular constraint, right? So max are the specs, but the means are basically from the Pareto frontier. Yeah, good question. So yeah, so we basically show this frontier, but to actually get to this frontier, right? So there will be a lot of different design trade-offs that we consider. So that's why it's when you hear people talk design space exploration, it's basically, oh, how do we actually get to this frontier, right? All the different dots, and we talk about all the different parameters like BDD, sizing, topology, and also microarchitecture. All the things can have interesting implications and will affect the shape of this frontier. So it's hardware dependent, circuit dependent, device dependent. It's also microarchitecture dependent to actually get this optimization. Yeah, so as we mentioned, there could be different optimization. There are like many ways that we can actually do, right? And like the example we had before, this is voltage, this is sizing, or this could be like microarchitecture. And then this could be basically everything combined, right? We combined them together. So typically, in a lot of cases, why this kind of problem is actually hard, because they're actually multi-variable optimization problems. So CAD2 is actually pretty good at this these days, basically understanding the trade-off. And then a lot of questions in the CAD space is basically this kind of design space optimization to actually find optimal ones. Yeah, so we mentioned earlier, right? So now if we understand individual curves, we can actually get our Pareto frontier. This is basically the best we can achieve, right? And there are multiple also optimal. It could be optimal best performance. This could also be optimal best energy, right? To actually get the minimum energy, right? Again, depends on the metric, right? What we are optimizing for. We could also get different performance and energy. In a lot of cases, realistically speaking, yes, so that's what this slide trying to show, right? We either maximizing throughput, basically get the low performance, low latency, high performance with a given energy target, or we minimize energy for a given throughput, right? So what we mentioned, this is like a lot of processor design are like this, and this is more like a lot of things interacting with sensors are more like the lower design point. Any questions, comments? Make sense? Okay, yeah, so a lot of things in some sense are actually hidden these days by CAD tools when they think about optimization. But again, it's very important to develop intuition, right? So we are actually more focused on the intuition and understand this space. A lot of time, especially hardware designer, it's like we like to focus on like particular thing. You are, let's say we're understanding the topology. We want to have a new topology, right? We focus on the implications of our new circuit topology, but it's actually very likely you may actually miss some other components that also contribute significantly to the design space. So it's also just good to remind yourself, okay, I'm understanding these particular behaviors, but there could be a lot of other things that could also complicate the trade-off. Okay, so that's optimization, right? So we kind of hinted this before, right? There are many different parameters that we need to optimize, right? The different tuning parameters. What do we mean by that, right? Circuit level, we already mentioned, right? You can size your circuit differently, bigger or smaller, faster or slower. You can also change the supply. You can also pick different threshold voltage, right? Depends on your need. A different logic style, different standard library. Sometimes you may even want to do custom design and topology, right? We'll talk about the other example. There are different topologies in different functional units or schematic unit. You can also pick. And then at architectural level, right? We probably don't have time to talk about this today, but NASA has a very interesting study to actually evaluate the parallel versus pipeline architecture, right? So that's a microarchitecture, again, more tailored to processors. But if you just bring in like other flavors, like in order, out of order, bigger cache, smaller cache, like CPUs versus GPU, or even accelerators, right? All of those can actually be, it's more like just another parameter in this space. And what we really want to do, as a question asked earlier, right? So we want to have actually this global optimal performance and energy trade-off for a given function, right? So basically you want to get, this green curve is basically the Pareto frontier, right? Once we're actually combining everything, this is the Pareto frontier of our design, right? So this is what we want to do, and a lot of time we're basically, this is basically the design space exploration problem to trying to understand the implications of different parameters and how we actually navigate this space. Okay, so that's basically the big high level motivation. We'll actually go down to how briefly talk about the microarchitecture component. Next lecture, we'll also talk about especially VDD, both sizing and supply voltage. These are very important in actually at the circuit level to optimize for different energy efficiency curve. We will come back again, especially VDD, it's a very important trick, very powerful. So it's very important to understand its implications. Before we move on, questions, comments, thoughts? Okay, so we see the space, right? What's the space that we're talking about when we come to optimization? Again, one thing I like to remind my students is that it's very easy, just, we focus on supply, or sometimes we focus on like how we can do pipelining, but there are just many other things, right? Don't lose the big picture when you think about the optimization. Sometimes it's actually, if you just change to a completely different topology, you have a very different trade-off. The takeaways that you have may actually not apply anymore. So always keep that in mind. So last, I want to actually briefly talk about, so we talk about like CAT is actually doing this kind of optimization, right? What kind of, this is actually can be viewed as a standard optimization problem. You have different trade-off with different parameters. So it's briefly how we actually, how a CAT will actually understand this space. So what they're trying to do a lot of time is basically they want to like in search for an optimal design, right? So the goal is to actually get an optimal design. And there are so many different trade-offs in this space. Like we mentioned earlier, you were just focusing on the circuit level, right? So we could actually do, let's say, like we can do the VDD, like one of the parameters of VDD, another parameter, let's do sizing, right? So that's the things we're going to cover next. So those are the parameters that we have in this space, right? Well, we can keep one parameter, keep a fixed VDD and the changing sizing, or we can keep a fixed sizing and then change a VDD, right? So you will actually start from a particular point and how we would actually navigate this space, right? So the way we actually navigate space is basically, in some sense, actually very similar to if you you take some machine learning class. A lot of this optimization is very similar. It's basically trying to do this kind of gradient descent, right? It's trying to understand the slope of change and to see whether we actually get to an optimal point, that kind of the balance, right? So we'll hear people talking about the sensitivity. It's basically trying to understand the slope of change. Let's say for A, right? So this is sensitivity of A. It basically the delta here, energy over the delta delay, right? Delay and delta energy, right? So this is slope of change for A, right? Because we're changing A parameter here. And then we can also evaluate sensitivity of B, right? So the yellow curve is B, right? We're fixing A and we're changing B, right? So again, the delta energy divided by delta delay, right? So that's a slope here, so, right? So with this, you will see, okay, so in this, we can either change sizing, right? Get a bigger, get a different design point. We could also change what's B, VDD, right? Get another design point. When we actually do this kind of optimization, so once we have the slope, we typically want to get a balance point so that we are actually, things are minimized, right? So we don't need to change, right? So in this case, let's say if this is where we start with, right? And we see actually a pretty significant change, a bigger slope that we have in B versus A, right? What we can always do is basically similar to what we do actually gradient descent. It's basically, we want to actually get to a potentially better design point. We can either start with A or start with B, right? So here I'm just starting with A. We can actually follow the slope of A to get to a lower delay point. Then once we get to the lower delay point, we can also follow the slope of B to actually get a further lower energy point. So here we can actually basically shift the design to actually get a better energy and delay frontier compared to where we start with. So typically, similar to the gradient descent, we basically want to have like similar sensitivity, so it's actually more balanced. Otherwise, you can still actually follow, let's say, one of the slopes to actually get a better design. So right, so we want to basically, once everything kind of settled of similar sensitivity, you kind of basically reach your energy delay optimal space. Again, this is more just some iteration to keep track of. We'll actually talk about more specific example with, especially with supply, because they're so important, how we can actually take advantage of that to navigate this space. But then this is basically how we do this as an optimization. A lot of CAD tools basically do this internally to actually understand the space. So a lot, very abstract so far, again, to understand the principles, but I do want to actually bring maybe a little bit more practical aspect, right? How this energy delay trade-off is actually being used in modern processors. So we talk about the like the big little style architecture of different trade-off. So around 2010, that's actually when the big little processor actually already came up, right? So now we're very interested to understand this fairly complex trade-off of both energy. Again, the lower, the better. So here we're actually doing performance. So performance is actually the higher, the better. So one thing I like to do whenever I see this, this kind of plot is always look at the axis and to see whether it's the lower the better or the higher the better. Otherwise, you're getting completely different conclusions. So for this plot, this is actually the optimal space, right? We want to have lower energy and the high performance. So we want to be here, which is different from the delay curve. We want to be the lower left. So this is the performance I want to do. So this is basically an exploration to actually evaluate the different microarchitecture constraints, right? So we see the different constraints like different in order or out of order processor. We can also change issue weights here. This is actually a more detailed breakdown. We can also the cycle time, right? In terms of fan out of 4, right? Dictate frequency and a range of different parameters, branch predictors, cache size, different latency associated with front end, compute, and also low store queue, right? All of those are actually very important. So this is basically an example of what people call design space exploration, of evaluating those different space. And then, like earlier question about why we cared about this curve, right? So when you actually consider those parameters, you'll get like a range of curve like this. So this is basically the best you can get for this space under different constraints. So with this, again, a very dense plot, a lot of details here, but one of this is basically imply this kind of big little architecture here, in the sense that this is basically each of the curve, the black one is for all the out of order, and the blue one is for all the in order, right? We see a similar pattern in the sense you will really care performance, this kind of high perf case. Only out of order processors can actually deliver those high performance, right? Only black curve can actually deliver those super high performance. So if we actually care about that region, we need to have out of order cores, we need to have the big cores. But then we actually come to the left region where the performance limit is less constrained, but we are actually more constrained by energy, or care more about energy. And then we see those in order solutions are actually on the frontier. So you will actually do a global frontier. So it's more like this, right? So on the high performance range, auto order core on the frontier, and in the low performance case, roughly the in order, the blue curve are on the frontier, right? So this is basically a global design space, and then we look at different design choices, right? So a couple of things highlighted here. So first, I find it very interesting. If you look at the L1 cache latency, almost all of those, no matter whether it's in order or out of order, it's always 1. So this is basically always 1 cycle there. They're very sensitive to cache latency. This is actually pretty impractical. Like L1, like 1 cycle L1 cache latency is just very short. So typically it's more like 3 or 4 cycles. But again, to get to the frontier, get high enough performance, very sensitive to cache latency. So that's also very important. Another one I like to highlight is cache size here. So So typically, especially instruction cache size is pretty big. I think they're sweeping this range like from 2 to 64 or something. They always pick like large enough 32 KB cache. Even for D-cache, it's also more on the larger side. So cache performance is also very important, and we'll always need actually big enough capacity here, especially instructions. So Google these days actually have like request special processors because they are so sensitive to instructions. They actually want even bigger instruction cache these days. So some of the special processor they design, Intel design for Google, is actually have even bigger instruction cache because they're just so front-end bundled. Another one is cycle time in terms of the 4, right? Remember what we showed earlier in even the 2000 range, we're talking about 7 or 8 out of 4 delays, right? For those pipeline depths. But now when it comes to actually more realistic modern processors, we are roughly in the 15-ish range, no matter for in order and out of order, right? So those are actually more standard. We're not pushing that crazy to the super high frequency processor these days. So yeah, so this is basically an example of putting this together, how this can actually help us to understand this trade-off in this space. Again, we talk about different metrics, different energy delay, different ways of evaluating those, and different trade-off in this space, and different optimization goal, right? We're optimizing for performance or energy. Next, we're going to actually dive deeper. We'll do that next lecture. To especially, I already hinted into this lecture, right? VDD is very important, how we can actually understand the implications of voltage and how that scale correlates, how scaling VDD lead to better either energy or performance or delay there. And we also want to see the parallelism and pipelining implications when it comes to low power design. So with that, this is the end of today's lecture. Great to see you all, and we'll continue our energy discussion next week. Okay.